Good morning, class. Good morning. No, really. Good morning.
Good morning.
All right, today we'll be discussing Newton's laws of motion. We're basically going to give you examples of each law of motion and tell what each one states individually. Newton's first law of motion states, objects remain at rest or in uniform motion in a straight line unless compelled to change the state by action of an external force. This basically means that an object in motion will remain in motion unless another force is acted upon it, and the same thing for rest. Newton's second law states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. The equation basically shows you that force can be calculated by multiplying mass times acceleration, and if you're given a mass and force, you can calculate acceleration by dividing force by mass. Newton's third law states that for every action there is an equal and opposite reaction. This basically means that for every force applied to an object, there will be a force in the opposite direction, which would also be applied to that same force.
Today we're going to do Newton's third law, which is inertia, which simply states that an object in motion sends the same motion unless acted on by an outside force, which is also the same when an object is at rest, unless acted on by an outside force.
All right, ready? Go.
Okay, so as we were taught in the lesson, we learned that Newton's second law is the law of force. And how the law of force is defined as is force equals mass times acceleration. So in this project, we're going to determine the mass of the ball and how fast it accelerates going down into the ground. We're going to use that with the addition of gravity. All right, 3, 2, 1.
Storm the people.
Run routes, tough matchup.
Here comes Brady, and he's got the. He needs some milk.
Oh my gosh,
He needs some
that
milk.
was easy. The speed of Greg Hardy, premier pass rusher in the NFL.
He needs some milk.
He got right around Nate's shoulder.
There's a good starting left tackle. This will make the Patriots
He needs
think
some milk.
about now, what are you going to do on the offensive side, Jim? Maybe put a formation there?
He needs some milk.
Because if you match him up one.
The third law of Newton states that if a body exerts a force on a second body, the second body is going to exert a force that is equal in magnitude and opposite in direction to the first force. So for each action, there is a reaction.
Okay, go. That was Purdy.
In order to find our force of the ball in our ball drop experiment, we used our three givens. We have our initial height, which is 21.29 feet, which is equivalent to 6.49 meters. We use our time, which is 1.38 seconds, and we use the mass of the ball, which is 0.3529 kilograms, and we're here to find our force. In order to find our force, we use the formula y equals y initial plus the initial velocity in the y direction times time minus 1/2 gt squared. We cross out y because our y final will be 0 and our initial velocity of the y will be 0. So now we're left with 0 equals y naught minus 1/2 gt squared. Now we're here to find our g. So that leads us to g equals 2 y initial over t squared. And now we simply plug in our givens. Now we're left with g equals 2 times 6.49 meters over 1.13 seconds squared. And we're left with g equals 10.16 meters per second squared. G is equal to A. So we plug in our A into our force formula, which is force equals mass times acceleration. And so force equals, as we plug in our givens, 0.3529 kilograms times 10.16 meters per second squared. And we end up with a result of 3.59.
For Newton's third law, we calculated the force applied from the pool stick to the cue ball and the force applied from the cue ball to the ball rack. We know the force equals to mass times acceleration. For the mass, we found the mass of the pool stick, which is 0.5699 kilograms, and the mass of the ball equivalent to 0.156 kilograms. We calculated the velocity of the stick as it hit the ball. Velocity equals to distance over time, with the distance of the ball equaling to 0.0558 meters. The time it took for the stick to hit the ball was 0.15 seconds. The velocity came out to be 0.4656 meters per second. We then calculated the pull stick acceleration, which is v over t, equaling to 0.4656 meters per second divided by 0.15 seconds, equaling to 2.483 meters per second squared. We repeated this process for the ball hitting the ball rack. The distance of the ball rack was 2.5 feet converted to 0.76 meters, and the time of the ball hitting the rack was 0.18 seconds. We solved for velocity by dividing 0.76 meters by 1.18 seconds, equaling to 4.233 meters per second. We calculate the acceleration by dividing the velocity by the time from the ball hitting the rack, equaling to 4.233 meters per second meters per second, divided by 0.18 seconds, equaling to 23.5183 meters per second squared. Now that we calculate the acceleration of the pull stick and the ball, we can calculate the force of the pull stick applies to the ball and the force of the ball applies to the rack, equaling to the force of the pull stick being 0.5699 kilograms times 2.483 meters per second squared, equaling to 1.415 newtons, and the force of the ball hitting the rack equaling to 0.156 kilograms times 23.5185 meters per second squared, equaling to 3.67 newtons.